Okay, so welcome to an overview of calculus concepts. I found this site, and what we're going to do is we're going to start identifying concepts that calculus uses. So let's just get started here. We got functions, and I'll make these all singular. We have the domain and the range of a function. So the function domain and the function range. Put that on a new line to emphasize range. Intervals and interval notation. So there's lots of notation. Different people from around the world doing things differently. It's not always the best thing, so coming up with notation is probably helpful for communication. So you have something called an interval, and along with that we have something called the actual interval notation. Even and odd functions. Some functions are even, some functions are odd. Let's add that here. We'll just add that as one, even, odd function. Function graph transformations. Vertical and horizontal shifts. Okay, so we can add the vertical or horizontal shift, and then the function graph transformation. You know, and they introduced function graph. I don't know what a function graph is, so let's make that function graph, and we'll add a function graph transformation. So usually transformation is taking data, manipulating it, moving it around, changing things into something else. Function graph transformations, this is another part here. Stretching, reflecting, and compressing. Okay. So what do we need to do? We're going to need to stretch. And we might circle back to this. We need to reflect. And then we'll need to compress. That may be common amongst calculus concepts. We have combined transformations. I'm going to skip that one. Function graphs, there we go. Arithmetic operations on the functions. Composition of functions, one-to-one functions, lots of function stuff. Linear, quadratic, and cubic function models. Okay, so that's a good one. We have a linear function model, a quadratic function model, and a cubic function model. Now remember, as I'm saying these, I pause just a little bit between concepts, and I want you to repeat those. Say them either in your head or out loud or both. Don't just listen to me. This is supposed to be a training exercise for you to not only hear the words spoken, but to actually contribute and speak them or think them afterwards. So linear function model, quadratic function model, cubic function model. We have an exponential model. So when I say exponential model, you say exponential model. composition of functions. So we can simplify that and just say function composition. Arithmetic operations, we're going to skip that one because that's, arithmetic is, something that a lot of people have familiarity with. So that completes the function graphs and models section. Let's see what's down here in limits and continuity. Limit, that's a new one. Limit. Introduction to limits, one-sided limit. Properties of limits, limits involving infinity. Limits of polynomial and rational functions. Limits involving radical functions. Limits involving trigonometric functions. Composite functions. Continuity of a function. So actually I'm going to jump straight to that one. I like that one. Function continuity. And I say function continuity. You say? Alright. Function continuity. Properties of continuous functions. So we have a lot of things here. So let's go ahead and get started. Continuous function. Trigonometric function. Polynomial function. Radical function. We have limits. There's our limit. But it looks like there's one-sided limits. And everything has a property to it. So limit and its properties. I'm going to skip properties. Limits involving infinity. So we have polynomial function, rational function. Oh, there's radical function and rational function. There we go. What is rational? What is radical? We have our trigonometric composite function. Now see down here they say continuous function. So there must be an also composite function. But here we've already collected function composition. So that's interesting. For now, we'll add it as a composite function. Alright, so let's move on to the next section here. Lots of limits and limits involving these types of functions. So because it's such an important kind of introductory thing here, let's bring that up here. The limit, very important concept in calculus. I'll just move that down here. There's no order to these. We can arrange as we like. Now the derivative. Alright, that's a good one. Derivative. Related rates. Finding maxima and minima or extrema of functions. So if they're grouping those together, we can group them as well. Call them function extrema. And that, I'll put it in parentheses. Maxima, minima. Fancy words for maximum and minimum. There we go. Mean value theorem. How many are there? We have 11. We'll just go through these. Again, if I have a pause between my words, please say them aloud. So mean value theorem, first derivative test, second derivative test. I don't see a third derivative test. How to use them. And there's something called an indeterminate limit, L'Hopital's rule, function graphs, linearization of a function. Okay, so let's get started here. So we have the mean value theorem. We have the first derivative test, and I'll leave these as separate concepts because perhaps the second derivative test is quite different. Maybe it's similar. We don't know. At this point, we don't know. And then we have an indeterminate limit, which is be a type of limit. So there's probably many different types of limits. In this case, it's indeterminate. Makes me wonder if there's an determinate without the n at the beginning. We'll find out. And then we have L'Hopital's rule. The fact that it has rule sounds like it's important. We have function graph. Oh, we have function graph over here, so we can skip that one. And I do want to know more about optimization. I wonder if it's specific to derivative optimization. I don't really like that because it's pretty generic. But there's also linearization of a function. So let's do this. Let's do function linearization. Let's go back to here and do function optimization. I bet they're related. And then approximating roots of a function, Newton's method. So if a function has a root, so we have a function root, and then Newton came up with some kind of method. We'll find out later what that is. Method, Newton's method. All right, so that's pretty much the 11 derivative related applications. Let's move on to integrals. You notice the S meaning plural and the gration meaning the topic of how to do something, the process of something, integration. But that is a new one, very important, integral. Ooh, antiderivatives, indefinite integral. Well, we had an indeterminate limit, but we didn't have a indefinite limit. That's interesting. All right, well, anyways, we have antiderivative. So we have derivative and antiderivative. It makes me wonder if there's an integral and anti-integral, or a function and anti-function. I don't think there is, but something fun to think about. We have the indefinite integral. Indefinite, meaning goes on for a long time. Associated with infinity, I believe. And then we have the differential equation. So we have lots of equations. In this case, it's some equation related to derivatives, and let's call it differential equations. Indefinite integration, indefinite integral. So what I can do here is I can do integral, integration. There we go. And I think I had something similar prior. Interval and interval notation. I'm going to leave. I'm just going to put, notation is such a important topic. Whatever it is, just stick notation at the end of it. And probably has its own following. Alright, so we're back to differential equations. Change of a variable. So we have this thing called a variable, and somehow it changes. Up, down, I don't know, high, low. Estimating area under a curve. That's an interesting concept. Area under a curve. You have this thing called a curve, and there must be some area underneath. Ooh, what's this one? Finite Riemann sums. Sounds important. Finite Riemann sums. The definite integral. Okay, so we did have the indefinite integral, and now we have a definite integral. And I'm guessing there's definite integration, so let's go ahead and put that on there too. Now here's the limit of a Riemann sum. Finite Riemann sums. And the limit of a Riemann sum. So, sounds like Riemann sum needs to be on its own. What is the Riemann sum? If you know, toss it in the comments. But we have a finite Riemann sum. And so I'm going to get rid of that. And then we have a limit of a Riemann sum. So we have the Riemann sum limit. And again, when I say Riemann sum limit, you say Riemann sum limit. Definite integral, we got that one. Fundamental theorem of calculus. Ooh, that one sounds really important. Fundamental theorem of calculus. Some basic properties of definite integrals. So we have the definite integral here. And I like, you know what, I kind of like doing it this way. There we go. Let's do that. The fact that it can fit all in one line, at least. Yeah, there we go. Integral, integration. Indefinite integral. Do we get the concept of integral here? But do we have the concept of the process of doing something? Integration. I think we do. You know what? So let's do this. Stay true to our efforts here. And let's go ahead and put integration. And we'll just get rid of this. There we go. So we have something called the indefinite integral. Something called the definite integral. And they can both be involved with integration. Alright, back to our list here. So we have the Riemann sum, the limit of the Riemann sum, the fundamental theorem of calculus. Alright, so definite integrals, it's properties for everything. So leave that one alone. The mean value theorem. Okay, here's another theorem. Now we had a theorem earlier. You remember what that theorem is? Mean value theorem. There we go. So the other theorem was We got the fundamental theorem of calculus, Newton's method, L'Hopital's rule. Mean value theorem up here. So we already have that one. So we'll change this one down here. Change of variable, numerical integration, trapezoidal method. I'll do, and there's 2 topics on that, so it must be relatively important. Numerical integration. But I'm guessing there's many types of integration, not just numerical. Trapezoidal method. Makes me think there's other types of methods too. Rhomboidal, trigon, basically 3 versus 5 versus 2. We'll see. Simpson's rule. So we have another rule here. I don't know who Simpson's is at this point, but Simpson's rule. Okay. All right, so that kind of covers the integrals and integration. Let's move on to the application of the indefinite integral. So we have area between 2 curves. You remember earlier we had the area under a curve, but this time it's the area between 2 curves. So what things can you do with 1 curve? What things can you do with 2 curves? Volumes by cross section. Okay, so if you're not that familiar with volumes, you should know what a volume is. And then we should know what a cross section is. Now there's 1, 2, 3 solids of revolution. Wow. So that's pretty cool. Sounds important. Revolution solid. What is a revolution solid? Volumes by disk, washers, or cylindrical shells. So you would need to know what a disk is, a washer, cylindrical shell. Again, I say cylindrical shell, you say excellent. Plane curve. That's interesting. Now we have the length, the width, the height. There's all kinds of properties of a plane curve, but the question I'm asking, what is a plane curve? Area of a surface of revolution. Now see up here we had solids of revolution. Now we have this concept of surface of revolution. So that would be revolution surface. Applications of work and force. Now if you've been in the physics, studied a little bit of physics, you'll see the pretty particular about what work is and what force is. Now we have different types of forces, looks like. We have a fluid force. And we have probability and the probability density function. We have just a little bit of distribution, odds, maybe this, maybe that, possibility, prediction type concept here with the probability density and a probability density function. So when you see this stuff, probability density is one concept, but the actual function of the probability density is a slightly different version of that. Okay, so we're doing good. Transcendental functions. Ooh, that's a good word. Let's put that up here. Sounds important. Transcendental function. Again, another type of function. Inverse function. Exponential function, logarithmic function. Now we have exponential function here. Did we get logarithmic function? We got polynomial, but logarithm, the log is different. So let's do logarithmic function. There we go. Now we have derivatives of those and integrals of those. But because there's so much involved with the integral and with the derivative, let's just make the convention that if we have a logarithmic function, there's going to be some integrals related to that. If we have an exponential function, or polynomial function, there's going to be derivative or integrals related to that. Did we get the exponential model, but did we actually get the exponential function? I don't think we did. There's a difference between exponential model. There's a difference between a model and a function. In this case, we found the exponential function. All right, exponential growth and exponential decay. So I think just the concept of growth would be important, and the concept of decay would be important, because there's different types of growth, there's different types of decays. In this case, it's exponential growth and exponential decay. So there's probably logarithmic decay, polynomial decay, but it may not state these in this author's list here. All right, inverse trigonometric function. So we had a trigonometric function, I believe, but now we have the inverse of it. Inverse trigonometric function. The derivatives of that, the integrals of that, so that's a very important one. Inverse trigonometric function. All right, now we're on to hyperbolic. Hyperbolic function. What is that? And the derivatives and integrals of those. And then the inverse hyperbolic function. I almost wonder if there's an inverse of all these functions. Sure sounds like it. And then the derivatives and integrals of the inverse hyperbolic functions. Okay, so that's the transcendental functions. Moving along here, like we have some more integration techniques.